All right, hi everyone. Let me start by thanking the organizers for creating and setting up such an awesome and engaging program. And in this talk, I'm going to propose a link between the gravitational wave merger of stellar mass black holes and the formation of Gaia BHs, where I have a star on an orbit, a detached star on an orbit around a stellar mass black hole, and the natural formation of low mass X-ray binaries. And I'm going to predict that shortly after the gravitational wave mergers, in some of the cases, we will have an electromagnetic counterpart. All right, so let us think for a second, how do we actually detect black holes, see stellar mass black holes that emit no light? So, very time-honored method is to catch a black hole in the act as it's eating something. These are X-ray binaries. In this talk, I'm going to focus on low-mass X-ray binaries, but the extension to high-mass X-ray binaries is really natural. Another way to detect stellar mass black holes is through gravitational wave emission, really transform the way that we sense our universe because we no longer rely on the electromagnetic power spectrum. Not power, just spectrum. Another way is, of course, the Gaia BHs, where we really detect the motion of a star around an unseen companion. All these three ways are methodologies to detect black holes, rely on binaries, and each of them bring their own challenges in forming them. There have been some ideas whether or not there's some connections between these three sources. Maybe there's some connection in trying to understand why the masses of the black holes in low mass X-ray binaries seem to be different, maybe from gravitational wave emission. What about the Gaia BHs? But as far as I know, up to now, there hasn't been a suggestion to connect all three of them. There is, of course, another way to detect stellar mass black holes, and that relies on microlensing. And while I'm going to mainly focus on the binary channel, the channel that I'll describe to you produces a lot of singles black holes naturally detected by microlensing. So I'm going to suggest a link between all these four methodologies. All right, so the plan for this talk is to describe some possible formation channels. I'm going to be really cherry picking here, so if you don't see your favorite formation channel, apologies. I'm going to really I'm going to talk about formation channels that will help me describe the physics that I want to talk about. And then I'm going to propose the connection between all of them and describe my prediction. All right, so let's start. I'm going to start with low mass X-ray binary. And I want to describe a simple two formation channels. So first thing first, we need a binary, duh. That's good, because most, if not all, of massive stars reside in a binary configuration. All right, so we will have, here is a binary, we have a massive star, the progenitor of the black hole, and a low mass star. And then what happens is that as the massive star expands due to post-main sequence evolution, we enter the common envelope stage that shrinks the orbit, usually shrinks the orbit of the low mass star inside. I'm going to really describe it in a very heuristic way. There are lots of experts in the room about this, but the main idea is that since we change the orbit, we have an energy exchange. That means that it goes in the expanse of the envelope. If there is enough energy to eject the envelope, at the end of the day, we're left with a helium star and a low mass star. And if, there's another if here, if at the end there is some supernova, maybe there isn't, maybe there is, there are lots of debate about it in the literature, if there is enough, and maybe there is some natal kick to shrink the orbit even more. At the end of the day, we get a black hole and a low mass star on a short amount, or not a short, just a short orbit. And then we need to wait for the low mass star to go through its post-main sequence evolution and create low mass X-ray binary. All right. So this is very heuristic, the binary channel to form low mass X-ray binary. Cool. Then we thought, why not do it with triples? Okay, so if your thought right now is, come on, Smadar, why triples? That means that you don't know me and my obsessions with triples. But here, actually, it's unavoidable. I cannot do without it because most of massive stars reside in a triple configuration. I'm not changing nature here. So here is the triple fraction as a function of the primary mass. This is a paper by Offner et al. And we can see here the massive stars, most of them are in triple configuration. So we have to consider it, whether we want to or not. All right, so now let's think about what does the triple does for us, if anything. So here is a triple. This is a way to examine this triple system. In order to get a stable system, we need it to be hierarchical, meaning two stars orbiting on a tight configuration and another one far, far away. This system was studied well for a long time. I'm going very, very quickly describe what is happening here. Because of this separation of scales, I can smash the mass around the orbit and treat it as two wires that interact with one another. This was studied back in the 60s by Kozai and Lidov, and nowadays it's been really popular, not just in science, but also in the public, maybe because of the show or the books, which are good, but a little spoiler alert, and sorry for spoiling, but in the books and the show, it's not really the three-body problem, it's the four-body problem, 3 stars and a planet, completely different dynamics, so we can ignore this thing. But it's kind of cool, and what was shown back in the 60s is that the outer orbit torques the inner orbit in a manner that is similar to what we see here. So there is a little cartoon that shows the torquing. When it's less inclined, it's more eccentric, more inclined, less eccentric, vice versa. This type of a system. They also found a conservation law, and we can see it here. I can write the eccentricity of a system as 1 minus eccentricity square. So when I have, when something is aligned, right, I have a radial motion, I have zero eccentricity, zero angular momentum, so eccentricity of 1. So 1 minus eccentricity square, and then cosine I comes as present when I project something on the total angular momentum. Total angular momentum is conserved. This is a spherically symmetric system, of course. And we can see here, less inclined, more eccentric, more inclined, less eccentric. To make a very, very, very long story short, we showed that there was a problem in the 60s calculations. This is not correct. It's only correct only if one of my stars is a test particle and if the outer orbit dominates the system, dominates the potential, and it's circular. So I'll have an axisymmetric potential. Only then this system then has this conservation law. So we rederived everything. We call it the eccentric Kozai-Lidov mechanism that allows to the orientation and both the orientation and the magnitude of the angular momentum of both orbits to change. We expanded to the next level of approximation. There is a perturbation series. In some of the works that I'm going to show you, we also went to the even follow-up, the hexadecapole level, because that made a difference. And the system, we can tap to a large part of the parameter space. The main problem with the 60s calculation was that you really needed to fine-tune the initial conditions to get anything interesting happening. And we all know if we need to fine-tune something, that probably doesn't work for most of the system. So now we don't need to fine-tune anything. You get it all the time, actually too much. The system is very exciting. It's really rich, and it's also chaotic. I can also flip things from below 90 degrees to above 90 degrees, what I couldn't do before because I couldn't change the sign of the cosine. All right, so here is just an example to drive home this message of the new stuff. This is the inclination of the system. The eccentricity of the inner orbit is 1 minus e, because I care about the pericenter passage. As a function of time, we can see here these oscillations between inclination and eccentricity similar to what was said before. Here it's below 90 degrees, above 90 degrees, below 90 degrees. And this is in comparison to the 60s calculation, and you can see that it's qualitatively different. So it's really not the same of what was done, what was thought. So this is why it's important. And for us, we care about these extreme eccentricities. Remember, I'm trying to explain low mass X-ray binaries. I want to smash things together. I need a small pericenter passage. This is where I need to be, and we had a lot of studies to really understand that these high eccentricities are pervasive throughout the parameter space. So all is good. So now let's go back to see how that helps us with creating low mass X-ray binaries. So what we've done, and that was almost a decade ago, we tried to understand how we can do it with no common envelope. So we ran this eccentric Kozai-Lidov. We added general relativity, we added tides, and we added post-main sequence evolution using SSE. And here is an example of the population that we ran. This is inclination, eccentricity. We see the hallmark of this Kozai business. And here, this is the semi-major axis as a function of time. We can focus on this red line here, and this is a zoom in. We created a low mass X-ray binary. Yay. I was very happy. Most of the community ignored this work. Fine. It's okay. This happens. Until last year, where Karim and company found a friend to a very famous low mass X-ray binary V404 Cygni. And we can see it here. So then, together with Cheyenne Shariat, who's over there, he was an undergraduate at UCLA. Now he's a graduate student at Caltech. And with Karim and with Vicky, we revisited this idea, this time using Poseidon. The idea of using Poseidon means that we will be able to follow the post-main sequence stellar evolution of the massive star more accurately. And here, Cheyenne, this is a plot from Cheyenne's paper. This is semi-major axis. Pericenter is here in gray. Inclination, look at the green one. And this is the radius of the stars. This is where the black hole formed as a function of time. We see here flips, hallmark of this behavior. And here we get a low mass X-ray binary. Cheyenne found that it's actually very efficient to form black hole low mass X-ray binaries without common envelope. And it seems that V44 formed this way and without or with very small needle kick, which is an important factor that we can consider a little bit later. I want to highlight an interesting follow-up that was done recently by Ziyuan Chuan, a graduate student in my group, taking Cheyenne's simulations, those failed low mass X-ray binaries, things that didn't form low mass X-ray binaries, evolved to become white dwarfs. So the star itself was too far away, evolved to become a white dwarf, but you cannot turn off gravity. You cannot turn off this eccentric Kozai-Lidov. It continues to work, again, whether you want it or not. And what Ziyuan showed, that after a while, you can push the white dwarf into the black hole and form an ultra-compact X-ray binary. And this is what he shows here. Again, 1 minus E, semi-major axis. And this is a high eccentric with gravitational wave with white dwarf dynamical tides really help us get this compact X-ray binary. It's interesting because it's also a multi-messenger system. So this is SNR as a function of time. We see here LISA, gravitational wave SNR, and we see here in blue the X-ray normalized, so they'll all appear in the same thing, in the same plot. Here we see a bursting signal. So in LISA, it can be observed as a bursting gravitational wave event here. And after a while, it can be seen also in LISA and as an X-ray source together. Ziyuan suggests that this type of channel can produce between 3 to 27 ultra-compact X-ray binaries. We have 20 observed in our galaxy. And 1 may be observed in LISA. So that seems to be promising. So what did I show you so far, actually? So far, well, maybe not. I've convinced you that triples have to be there, whether we want to or not. We cannot ignore them. We can form low-mass X-ray binaries this way without common envelope. We can efficiently also form ultra-compact X-ray binaries. But I haven't done anything about this connection thing. So let's go figure out this connection and where it comes from. So the other one that I want to talk about, and I'll start with Gaia BHs actually. And because that's actually the easier one to do. It's the easier because we don't really understand how to form it. The problem is our old nemesis, this common envelope that I mentioned before. Gaia BH1 reside at 1 AU, which is where the star itself existed. So how come this system did not become a low-mass X-ray binary? Or if the star started further out, how did it not, because of mass loss, extended the orbit? That's a problem. There's been some ideas in the literature to try to address it. It often needs some fine-tuning. Maybe we fine-tune when we eject the envelope, or maybe some fine-tune natal kick for the black hole. And we know that whenever we want to fine-tune something that's already said, that's an issue, especially because they are estimating that there will be 20,000 Gaia BHs in our Milky Way. So I need to get some sort of a channel that will be very efficient. All right, so that was Gaia BHs. Let's go to gravitational wave emission. Well, that deserves their own multiple talks about the ideas that people have in the literature to do it. So I'm not going to do any justice for it, and I think that we're going to hear more about it in the conference. But very quickly, the ideas that exist are maybe there is some dynamical channel. Maybe in the dense globular clusters, we can have black holes meet each other and merge. Maybe in galactic nuclei, either they assist with a supermassive black hole, or with some gas around, or with some sort of black hole capture. Or maybe hierarchical triples have been suggested. Kina would note that I have not worked on this for a specific reason. And then maybe isolated binaries. So this has either common envelope or the stable mass transfer. I had only space to put only the common envelope cartoon, so sorry. And then maybe chemically homogeneous ideas. So mainly cartoons here, just to highlight people that I'm sure are going to talk about this later. And in an uncharacteristic way for myself, I'm actually going to choose the isolated binary idea for this talk. And I'm going to paste my tertiary because I said that it's unavoidable. What do I mean here? I mean that I'm going to take as a proof of concept a smaller mass black hole, a smaller mass star here, sorry. So here is a star with a smaller mass that helps me advocate for the isolated binary here. This is mainly a proof of concept so we can see if anything interesting is going to happen. Yes, it will. But, and then because the main sequence lifetime of this one solar mass is long, it will allow for the isolated binary to take place, to merge, and cool things to happen. So maybe the first question that you ask yourself is, wait a minute, Smadar, you showed us with this cartoon, you had all this hype about the eccentric Kozai-Lidov. So what does one solar mass do for this inner binary? The answer is actually not much. In fact, this is what we call the inverse eccentric Kozai-Lidov mechanism. It's because the one solar mass angular momentum is not dominating the system. And what happens here is that the inner orbit torques the outer orbit. We can get all kind of cool stuff. We can get flips as well, and high eccentricities and instabilities. So when I will consider a population, I'll include all the relevant perturbations in the Hamiltonians. So rest assured it will be okay, but for now we can just consider it to not be so important. All right, so here is my system. I have a binary black hole. I have a star. I will let the binary black hole merge, and I'll ask what will happen to the star. So we know that when two black holes merge, if I have a if the mass is different, if there's some mass ratio interesting there, we will have a gravitational wave recoil kick. Interestingly, all of this now becomes a deterministic calculation. We can just calculate exactly what will be the effect of the kick. We can calculate the magnitude of the kick, the vector of the kick, the orientation of it, and what will happen to the star. So very heuristically, I expect two possibilities. One is some unbound orbits. I will claim these are my microlensing candidates. And second is bound orbits, and I'll suggest that these will become my Gaia BH-like objects. Let's start with an example so we can see where I'm taking it to. So here is semi-major axis as a function of mass ratio. This is an example where I choose the semi-major axis of the star to be about 12 or something AU. This is the pericenter of the star, and I'm just changing the mass ratio of the black holes so we can play with it and see what we get. For the fun of it, I'm also showing here what's the semi-major axis of Gaia BH1 and the pericenter of Gaia BH1 as well. So now I'm going to let them merge. There's going to be a kick, and I'm going to calculate what will be the new semi-major axis of the star and the new pericenter. And here it is. So in red, we see the new semi-major axis of the star, and in purple, it's the new pericenter. And you can see here, and when I saw it, I was very excited. We can see very naturally Gaia BH1 example. This was some system like this was maybe the second system I tried as a, you know, how you start with having a new project and you just play with it initially. This was my game. I saw it, and then I was commuting to work. I did it very early in the morning. And I was commuting to work. I was talking with my sister, and I was very excited. And I was like, I got Gaia BH, I got Gaia BH. And then my sister said, did you see a doctor about that? Apparently not. I still suffer. Apart from Gaia BH that are pretty cool here, there's these very high eccentricities that I get here. So let's show them in a little bit different way. So here I'm showing the y-axis as the closest approach in solar radii, so it's easier maybe to see. And I've plotted here the circularization radius. This is basically the tidal radius from which I would expect circularization to take place. And this is the Roche limit. Basically what this means is that here I will expect these electromagnetic signatures that I mentioned that we will have. So the prediction also comes here naturally. So what I want to do now is to basically show a population. This population, again, this is a very proof of concept. The idea here is to start a black hole, two black holes, with a distribution in angular momentum that is being taken from isolated binaries population synthesis, and to stick a star there that is being motivated by Cheyenne's work that included all the stellar evolution processes. So this is what we did. And here I'm showing the bound orbits. So this is the new eccentricity, the new semi-major axis after the kick, after everything, just to make sure that we haven't screwed up anything. So this is up to the hexadecapole, general relativity, gravitational waves, and also the recoil kick. You can see that naturally we formed Gaia BH1-like systems and a lot of Gaia BH-like systems. And we also predict a wide tail, long tail of wide systems that will be still bound. And if all of LIGO sources came from isolated binaries, we expect between 1 to 10% of Gaia BHs to form this way. Now, this is a funny if, I know, because it does not mean to claim that the Milky Way sources are, that LIGO sources are Milky Way-like objects. However, this will give us some sort of anchor to see if this is even worth anything. And actually, it seems to be very encouraging that even with this very crude proof of concept with one solar mass, we can get Gaia BH-like systems in a very natural way. So that was these ones. And another thing we found is that in some cases, we cross the circularization radius. And that's actually, not surprisingly, divided to 50-50. In 50% of the times, we actually were above the Roche limit and smaller than the circularization radius. That means that after hundreds of million years, 2 gigayears, I would expect the system to circularize and form low-mass X-ray binary when the star will evolve beyond the main sequence. And in other times, we found that in 50% of these times, we found that the pericenter passage is so small that it crosses the Roche limit. And here we expect something that is similar to micro-disruption event, micro-tidal disruption event. So unlike tidal disruption event around supermassive black holes, the mass of the black hole is small. The time scale, the fallback time scale, is much, much smaller, which means that we will have something that happens pretty quick. We will expect to have super Eddington behavior, lots of reprocessed photons, maybe something that will emit in UV or blue, maybe something like an F-bot. So this is the expectation that we have here. And that will take place between days to months after the gravitational wave merger. All right. So then we estimated very similarly that if all LVK sources came from isolated binaries, again, this is not meant to say that all, I just anticipate some questions. It does not mean to say that all Milky Way-like galaxy black holes are LVK sources, but as an anchor, we expect about 0.02% of all gravitational waves to have some electromagnetic counterparts after 10 days to a month. This is really encouraging because, first of all, if I would get here, I don't know, that 10%, that we could rule it out, right? Because we haven't seen anything. And 0.02% gives us hope for 05, 06 runs. So that's really good. So what did I show you? I talked a little bit about the challenges information channels. I know I was very, very quick there. And then I mentioned that maybe if I'll take a gravitational wave merger, for now just thinking about it in an isolated binary way, and stick a star there, the gravitational wave recoil kick can lead naturally to the formation of Gaia BH-like systems, of low-mass X-ray binaries. I also predicted that we will have an electromagnetic counterpart soon after. That connected all 3 binary sources that involve black holes together. And it also predicts lots of candidates for microlensing. And that's it. Thank you very much.
Okay, thank you for the great talk. I'm gonna try to prioritize people who haven't asked a question yet. So.
Great talk. Beautiful graphics, by the way, but let's talk about the science. I love your scenario for triples for Gaia. Are you assuming no kicks in the formation of the black holes to get these high rates? Because it seems...
Excellent question. So the question is about...
the kick you have is from the recoil, and so I think you need 0 kicks in your scenario.
Exactly. So I have 0 natal kicks in all of this. Natal kicks, in some cases, can break up the tertiary. Not in all. This is what we found with Cheyenne. And it actually raises an interesting question. Do black holes undergo or not undergo? How often do they undergo natal kicks? We know that there are some. For example, we see low-mass X-ray binaries with a residue of velocity beyond the motion in the galaxy. But for example, V404 Cygni seems to have very little or no natal kick. So I think this actually, right, instead of playing with it too much, at least in this stage of proof of concept, we assume no natal kicks. However, we are working on trying to extend this to a better understanding with the natal kicks. So, yeah.
the back. Who's next? Yeah, go ahead.
Thank you for your very interesting talk. I always enjoy your very nice visualizations and stuff. So you mentioned some fraction of, you can form these Gaia BHs with triple evolution. I was curious what fraction of LIGO sources can be affected by the presence of a companion. I guess it depends on their how close they are, and I don't think we know observationally. Do we have like any?
Wait, so your question is how many of the LIGO sources are affected by this channel?
Overall, like the presence of a companion.
So here, so 70%, and I assume that 70% are actually in triples, and that's a very big assumption. If there is no natal kick, if there is a natal kick, then we need to rethink about that. Maybe there is natal kick to everyone, right? And the V404 is the outlier. I think this is where, I think studies like this are the idea of trying to drive this a little bit to a more, to a better understanding. We do know that 70% of all massive stars are in triples. Therefore, this is where the 70% was taken. Did I answer your question, or was that?
Yeah, I was more asking in terms of their distance.
Oh, how far they are from us?
We don't know yet. Yeah.
No.
Okay, thanks.
I wanted to ask a follow-up question also on the BH-like ones. You know, Hans Hotterix. Gaia BH1 is very nearby, which implies it's a fairly common and banal occurrence in this scheme. Have you thought about whether this channel can occur frequently enough to make it plausible to find the result of such an evolutionary path so nearby?
So beyond the 10%, I'm trying to understand that question.
To find one within a kiloparsec of us, right? Which means there are vast numbers of them in the Milky Way.
Yeah, so this is where the anchor comes from. We thought it, sorry, I have to sit because I busted my knee and I'm just in horrible pain. So we have been thinking about this quite a lot. So if we assume that all LIGO sources, this is the anchor. If all LIGO sources are behaving like this, right? I have a triple and all of them coming, right? All of these systems coming from this case, I will get a 10%. 10% will form Gaia BH, and therefore I would expect that Gaia BH will be one of the 10%, Gaia BH1. 10%, whether or not it's a big number or a small number, I'm not sure. And the reason that I'm not sure about that is because this was such a proof of concept approach that in order to tell you is it 10% or 50% or whatever, I will need to do a full population synthesis, which I didn't bother to do yet because I thought, let's just see if it's interesting. I think it is.
So I had exactly the same kind of question, but now I think my question is going to turn into a comment.
Sure.
And then I have a different question.
A comment and a question.
Because the 10% calculation, let's take it at face value, but the rate of binary black hole mergers is for the whole universe.
Yeah.
If you translate that rate for our galaxy, and that rate is very, very small,
Yep.
and even that 10% for our galaxy, the calculation has not been done, but if you put together the Gaia selection effects and how close the system is, let's bet the rates don't match.
But the point is, Vicky, it's not about the rate, right? So I don't even need to debate with you.
But sometimes when it's orders of magnitude potentially different, it can be about the rates. That's a comment. Let me ask my question, Smadar. Okay. Let me ask my question. So going back to the triple occurrence, I want to ask whether we know the following. The low mass X-ray binary system, V404 obviously it's a triple. But it's a very different configuration than the triple with the potential triple with gravitational waves. So, low mass X-ray binary, very massive primary, low mass companion, low mass tertiary. Binary black holes, two massive stars, and then you're suggesting a low mass tertiary. From Offner's work or other work, what do we know? 70% triples of massive stars, but in what kinds of configurations and mass ratios do we have information?
Yes, I see Cheyenne grinning there. We actually do, Cheyenne. Do you want to answer it? This is a paper with the three of us, Cheyenne, myself,
I'll say we
and
understand it more in the low mass regime. In the high mass regime, everything that you see on that Offner plot stops at mass ratio 0.1 because we're observationally selected against not observing things with mass ratio 0.1 in whatever method you use. So I think we know nothing about the regime that even gives you the low mass X-ray binaries. For just binary evolution, how many 20-to-1 mass ratios? We don't know. So I think it's a critical future work to do that. For low mass stars, we understand it a bit better.
But I do want to say one more thing, Vicky. I think that the point of everything that I showed you was not to claim that all of Milky Way, all of the LVK black holes are coming from Milky Way-like galaxies. And it's just to show that there is, and it's just to show that there is some interesting connection there in a proof of concept, right? And maybe to seed some seeds for future works and interest to try to understand what exactly is lying there in the horizon. At least I think it was better to start it this way than starting to have a whole population synthesis before we know the answer. And I think the answer is encouraging, but to tell you exactly what is the rate, and that also relates to that and a question over there. Now I don't see you, there's like something in my, because I'm sitting. But this is why, anyway.
Great. This sounds like a great discussion for coffee. Let's move on to the next.
No, Reed already gave me the mic.
Okay, sorry.
Sorry, just a really quick comment about the rates. We actually did this calculation earlier in the workshop. We can probably share it with everyone. The Gaia-like black hole rate with black holes with low mass companion, the formation rate per Milky Way is 10% of the gravitational wave rate per Milky Way. Yeah,
cool.
These systems are really short-lived. The thing that I'm skeptical about is the masses, because we don't have a lot of 5+5 black hole mergers.
Oh, so with terms of the masses, what I try to do is I try to change the power spectrum. So actually, Maya, you asked me a question 2 months ago about the masses. And what I did since then is I tried to do the LVK power spectrum. I used all kind of masses that one can imagine. The results stay roughly the same. So maybe it's the opposite, right? Maybe we can, if the 10% does hold, which I'm not sure, but if it does, maybe it tells us something about the progenitor masses. So, yeah.
Okay, we have a little bit of time. You've been waiting.
Yeah, Jakob Stigmann from MPA. I have a question. I also really like the Gaia channel. And maybe I misunderstood, but you said based on the low mass of the tertiary companion, you assume that during the evolution towards forming the gravitational wave merger, it didn't really affect the evolution. But if we take the black hole masses or the black hole mass of Gaia for face value, we have what, maybe a 5+5 merging to a 9 or so, and the tertiary companion is really close, if that is the outer orbit that we are currently seeing. So I didn't really fully understand why the tertiary companion in that scenario is not heavily affecting the evolution towards the merger.
So two parts of the answer. One is part that I answered Maya when I tried to do it with different masses. Qualitatively, the rates stay the same. And the reason that it's not affecting so much is because the tertiary is further out. So I looked at what Cheyenne had calculated, and true, it was for one progenitor black hole and not two, but I took it as a inspiration to where to put the tertiary. The tertiary didn't start at 1 AU. It started way further. It came closer to 1 AU or to 1 AU because of the recoil kick. And then when it's further out, it's undergoing the inverse eccentric quasi-Lidov. In some very tiny part of the parameter space, it was enough of a lever to actually change the orbit of the inner ones. And this is something that we're going to explore more in future works, because that will also change the spins orientation, change the recoil kick. There's a lot of cool stuff more to do it there.
Okay, makes sense. Thanks.
All right. Thank you for a really great talk. And I think Vicky actually asked my first question also about the occurrence of the tertiary, but I'm sorry if I missed it, but I was wondering mostly there's a very strong prediction for the spins of the merged product, right?
Mm-hmm.
And so isn't there any way in which you can measure or exclude or see what the spin effect of coming in at a 0.7 spinning black hole in low mass X-ray binaries, but also in the Gaia black holes? And
so the spins, I want to say a few things about the spins. As long as the spins are not misaligned, if they're like this, the kicks will be very, very high. If the spins just align but high, it doesn't change the behavior so much. So this I can have high spinning, low spinning black holes. As long as they are mostly aligned through this isolated binary channel, then I'll be okay. This is relate also to the zero natal kick.
So the black hole that now is, it's already merged, and now you have a highly spinning black hole in a low mass X-ray binary in a Gaia black hole. So all of those should be 0.7 spins. Is there a way? I mean, low mass X-ray binaries, there's a whole discussion about whether they're spinning or not and things, but is there any way in which you could use that as an observable?
That's an interesting point. Now I understand your question. We can talk more about it. Cool.
Okay, I think final question, Salo.
Yeah, thank you for the talk. I have a question about the counterpart for LIGO binaries, right? Potential counterpart. So first of all, like you said, it's very low, so we're not in trouble. At the same time, I don't think anyone has been looking for months after our mergers, and so as long as you cannot predict when it would happen more precisely, not having seen a counterpart doesn't mean necessarily that there wasn't one, because I don't think many facilities have been following up our sky maps for weeks and months after. But the actual question I have is, have you put, at least at the toy model level, any model for, the tidal disruption and calculate a light curve and especially a range? Can we see those at 1 gigaparsec, 500 megaparsec?
Now I see your question. Very good question. How far can I see this electromagnetic counterpart? Probably not too far. That's the bad news about this. As we're very motivated by, there's several works in the literature. There's the work by Kyle Kramer. I saw him before somewhere. Here you are. He had some hydro works that can be motivated to that. And then there's some analytical work by Wei-Bing Liu. And both of these predict basically something that is in UV and blue, the blue part of the power spectrum, of the electromagnetic spectrum. So therefore, I suspect that we will not be able to see too far. So these are the bad news. Yeah, I got no good news here. Sorry.
Sometimes
but I need to somehow end this with a positive tone. So I don't know how to finish it now better.
Thank you.
Okay, I think I have a positive tone. We have coffee
All
waiting
right.
for us in the courtyard. So please join me in thanking our speakers again.